So quasi-linear equation, we know it is defined as P of xyz, zx plus q of xyz, zy is equal to r of xyz. The quasi-linear equations are defined like this. And if I call this as equation number 1, consider the quasi-linear equation in this form. Where this P, Q and R are continuously differentiable function of x, y and z. And this P square plus Q square plus R square is non-zero. That means simultaneously they are not vanishes. That means they are not zero together. If the solution of this z of xy define the integral surface in xyz plane, or in the space, I can say not now plane, it is a space. So its solution z of xy, which is a surface, defines an integral surface z is equal to z of xy in xyz plane or space in xyz space. Then what will be the normal to this, or I can say a normal to this surface? What is the direction ratio to the normal to this surface? So as we know, the direction ratio can be calculated by gradient. So the normal to the surface z is equal to z of xy has a direction ratio that is zx, zy and minus 1. Hence the equation 1 that is, you can see that here, that is PQR is a dot product with zx, zy and minus 1. So hence the equation 1 states the condition has a condition that the integral surface is such that at each point is the line with the direction ratio PQR is a tangent to the surface at that point. Why it is so? Because you just see that the dot product of this two, that means dot product of PQR into zx, zy minus 1. The dot product of this one will gives me P zx plus Q zy minus R, and that is equal to 0 as per the given condition. That means we have considered the differential equation like this. And the dot product of these two vectors is equal to 0, and z of xyz is one surface. So this will be gives me a normal to the surface. So this is in the direction of tangent to the surface. So that is the direction of the tangent to the surface that we can obtain from this. So in fact, any surface z is equal to z of xy is an tangent to the surface at point if and only if the tangent plane contains the characteristic direction. The characteristic direction means the direction PQR, which is the direction field defined by PD, which is a direction field defined by given PD at each point. Now we'll consider the integral curve of this field called the characteristic curves. Whatever the curve is, say that it is a characteristic field. So now we consider below the integral curves. Integrals, that means the whatever the solution curves. Integral means a solution curve of this field are called the characteristic curve. And they are family of the space whose tangent at point coincide with the characteristic direction at the point P, Q, R, and given by a system of ordinary differential equation, that is dx upon P that we have equal to dy upon Q equal to dz upon R equal to dt. Let's say this is dt. So this is actually a system of three linear equations is there. How? Because this can be represented as now is dy by dx by dt is equal to P, dy by dt is equal to Q, and dz by dt equal to R. So this is a system of linear equations is there. Again, by applying the existence and the uniqueness of the solution of initial value problem of ordinary differential equation, this solution for this one is passes through the characteristic curve through the point x0, y0, z0. So I will call this as equation number 2, or system of equation is a 2. So by the existence and uniqueness of the solution of the initial value problem for system of ordinary differential equation they are passes through a characteristic curve x is equal to x of x0 y0 z0 t, y equal to y0 y of y x0 y0 z0 t, and z is equal to z of x0 y0 z0 t through the point. So they are passing through the point x0 y0 z0. This system of ordinary differential equation have a solution is a two parameter family of integral curves. So the system of ordinary differential equation 2 being an autonomous system, and there will be two parameter family of integral surface. Integral curve, and hence this two parameter family of integral curve, every surface generated by one parameter family of integral surface, and for if we consider any point on such surface, then the tangent to the characteristic curve passing through that point lies on the tangent plane to the surface. And this tangent plane to the surface contains a line with the direction ratio, that is PQR. And hence the surface which we got, it is the integral surface. In addition to this, a converse is also true. That means every integral surface generated by a family of the characteristic curves is that. So every integral surface is actually generated by whatever the family of characteristic curves is there. That means every integral surface is nothing but the solution for this family of integral curves or characteristic curves. So that is the if and only if things we have. What we have discussed here, it is every integral surface generated by a family of characteristic curves, and a family of characteristic curves generate an integral surface. So it is if and only if things is there. And for that we need to have one theorem here, and that theorem says that when you will have a quasi-linear equation, will have a unique solution. Okay, so let us discuss that theorem. So consider the first order quasi-linear equation P of xyz zx plus q of xyz zy is equal to r of xyz, where p, q and r have continuous partial derivatives with respect to x, y and z. and p square plus q square plus r square is not equal to 0. So simultaneously all these three are not 0. Let the value x is equal to x0s, y equal to y0s, and z is equal to z0s be a prescribed along the initial curve. So their initial curve is given gamma 0, that is x is equal to x0 of s, y equal to y0 of s, and z is equal to z0 of s. And this x0, y0 and z0, they are continuously differentiable function in the interval AB. So x0, y0 and z0 are continuously differentiable functions in the interval AB. Further, we also required this thing, that is for A is less than or equal to S, less than or equal to B. If this quantity, that is d y0 by ds into p of x0 of s, y0 of s, z0 of s minus dx0 by ds into q of x0 of s, y0 of s, z0 of s is not equal to 0. If this quantity is not equal to 0, then there exists a unique solution z of xyz or z of xy defined in some neighborhood of the curve gamma 0, which satisfies the given PD. So it says that it satisfies the PD, and the initial condition whatever the initial condition is given, it also satisfies that, that is z of x0 of s, y0 of s is equal to z0 of s. That means the integral surface contains the initial curve data, that is the curve C that we have. So it is actually, this theorem is tells you regarding when the quasi-linear equation have a unique solution. Okay, so we'll not discuss the proof here for this theorem. The proof is easy, it's given in your textbook, but we are not discussing. We directly go for the example with that. So let's see once more what will be this result says. If you have given this quasi-linear equation and there is the initial curve is also given, and if this condition is satisfies, then we can say that the system or this differential equation has a unique solution. Okay, let us solve couple of examples with the base on this. The question is solve the initial value problem for quasi-linear equation, z is equal z of zx plus zy equal to 1 contains the initial curve c is equal to x0 is equal to s, y0 is equal to s, z0 is 1 by 2s, and for all the values of s is between 0 and 1. So to solve this one, what we can observe, first of all, we need to check whether this condition that we have here, it will satisfy or not. Okay. So we have here, first of all, we should note that comparing with p zx plus q zy is equal to r, we get p is equal to z, q is equal to 1, and r is also 1. Now we observe that dxy0 by ds into p, so you just see that what we have, dy0 s p minus dx0 by ds q minus dx0 by ds q. That value of p and q, they are also at the point x0 y0. So what is y0 we have? It is s. A derivative of that with respect to s will gives me 1 into p. The p is z. The value of z is 1 by 2 s minus x0 is s. A derivative of s with respect to s will gives me 1, and the value of q is also 1. So that will gives me 1 by 2 s minus 1. This will be never 0 for s is between close interval 0 1, because the value of s is between 0 and 1, and if you can see that one, this will be never 0. Now we need to consider the three differential equation, ordinary differential equation. So solving the following system of ordinary differential equation, that is dx by dt is equal to p, dy by dt equal to q, and dz by dt equal to r. The value of p we have given, it is from previously it is z, so dx by dt is equal to z, dy by dt is equal to 1, and dz by dt is equal to 1, because q is 1, r is also 1. So to solve this one, that means this equation, we'll have y is equal to t plus some another parameter s, or I can say it is a constant c1. The derivative of this one, that is t plus some constant c2. Why? Just it is easy to see, that is dz is equal to dt. If you take the integration, you will have some constant is there, and the value of z, if I substitute here, then it is dx by dt is equal to t plus c2. So it is dx is equal to t in plus c2 into dt. If I take the integration, that is gives me x is equal to x square by 2 plus c2 t plus c3. So finally what we have, it is x is equal to t square by 2 plus what we have, c2 dt, c2t plus some other constant c3. Y is equal to t plus c1, and z is equal to t plus c2. Now, initially we have given this three condition. initial conditions are that we have given it is x0 is s. So we have given x0 is equal to s, y0 is s, and z0 is 1 by 2 s. x0 means if I substitute x is equal to 0, y equal to 0, and z is equal to 0. So from this we'll get, we have three parts here. From this one, y of 0 is equal to 0 plus c1, but y of 0 is, so value of c1 is s. Here z of 0 is equal to 0 plus c2, but z of 0 is this 1 by 2 s, so the value of c2 is 1 by 2 s. If I substitute this value of c2 here, and if I use x of 0 is 0 plus c3, so the c3 value is s. So we have the value of this c1, c2, and c3. So finally what we have is x is equal to 1 by 2 t square plus, you just see that 1 by 2 t square. c2 is this 1 by 2 s, so it is 1 by 2 st plus c3 is s. Y is equal to, it is t plus c1 is s, so it is t plus s, and z is equal to also t plus s by 2, because c2 value is s by 2, so it is t plus s by 2. So these are the value of x, y, and z we got. Now we need to solve this three equation in terms of t and s. So solving, we need to solve these equations in terms of, solving this equation in form in s and t in terms of, solving for s and t in terms of x and y. We get, so we need to obtain what will be the value of s and t in terms of xy. So from last two equation you can get something from here. We subtract this two equation. If we subtract this last two equation, we have y equal to t plus s and z is equal to t plus s by 2. If I subtract this, t will get cancelled out. We'll have y minus z is equal to s minus s by 2. So that will gives me s by 2. So the s is 2 times y minus z. This is the value of s we get. But the z is also I need to convert in terms of xy. Now to get the value of t, what we can do? So we have y is equal to t plus s, and if I multiply the second equation by 2, and it is 2z is equal to t plus 2t plus s. Now if I subtract this 2, then we'll have y minus 2z is equal to minus t, and this s will get cancelled out. So the value of t will have y minus 2z minus of this. So it is, the value of t is 2z minus y. Now here unknown thing is this z, and z we need to convert into the terms of x. That is our objective. So we have z, value of z is equal to t plus s by 2, and the value of x is 1 by 2 t square plus 1 by 2 st plus s. You just see that from this to 1 by 2 t square, t is common out, you'll have t plus s, but the value of t plus s that we have, it is y. So this is y plus s. Now we need to convert this is in terms of y and z. The value of s is this. In fact, yeah, we got the value of okay. This is also we can do. No need to do this thing. No need to do this one. So what we got here is we got the solution, or we got the expression in terms of wait a minute, something is goes wrong. Yeah. So what we got the value. So what we have written here, we need to solve this equation for s and t in terms of, instead of I'm saying x and y, I have solved for y and z here. I just write down z and y, and we get this expression. And if I substitute this value of s and t in x, that means I have now x is equal to 1 by 2 t square plus 1 by 2 st plus s. I have the value of s and t now. I'm substituting that here. So t square is this 2z y square plus 1 by 2 s. The value of s is this, that is 2 times y minus z into t, that is 2z minus y, plus s, that is 2 times y minus z. So this 2 will get cancelled out. If you simplify this one, then it is 1 by 2 2z minus y square plus y minus z 2z minus y plus 2 times y minus z. So this is the surface, required surface we are looking for. That means the given surface is passing through this the initial curve which is given is passing through this surface. If you want, you can check also. Let us solve one more example. Find the integral surface of z into zx plus zy equal to 0 contains the initial data curve C, that is x 0 is equal to s, y0 is 0, z0 is f of s. where this f of s is defined like this: 1 if s is less than or equal to 0, 1 minus s if it is between 0 and 1, and 0 if it is greater than or equal to 1. So this is our problem. So first we need to check whether the solution is unique or existence. For that we need to have a condition. The condition that we need to check is, we observe that dy0 by ds into p minus dx0 by s into q. This we need to check whether this is non-zero or not. Here, what is the value of p we have? We compare with the equation p zx plus q zy is equal to r. The value of p we have z. So here p is z. Q we have, it is 1 and r is 0. And what is y0? We have given it is 0. So this is 0 into p, that is z minus z0. The z0 is this s. The derivative of s with respect to s is 1. Q it is 1. So this will gives me minus 1, which is non-zero for any value. So for every s, this is non-zero. So nothing problem with the solution is unique and it is exist. That is the things we have. So we need to consider the ordinary difference system of ordinary differential equation. System of ordinary differential equation. As dx by dt is equal to p, dy by dt is equal to q, dz by dt is equal to r. But dx by dt, the value of p we already obtained, that is z. dy by dt we have q, that is 1, and dz by dt it is r, so it is 0. So the last equation gives me the value of z, which is a constant. So let's say that constant is some value. So we have in the last one z is equal to c1. The second equation that we have dy by dt is equal to 1. So that dy is equal to dt, which gives me dy is equal to t plus c2. dx by dt we have given, it is z, but the value of z is c1, so that's why it is c1. So dx is equal to c1 dt. So x will gives me c1 into t plus c2. Now initially what is given? Initial conditions are x of 0, s0 is s, y of s0 is 0, z of s0 is f of t, f of s. That means we need to substitute t equal to 0 here. So the value of c1, so therefore with the value of c1 from this, because if I substitute this value, this will gives me z of c1 is f of s. This will gives me y of s0 is equal to 0 plus c2. So that means c2 is 0. The value of c2 will be 0. And from the last one we can have, it is s of s0 is equal to c1, that is f of s into 0 plus c2. But f of s0 is, c2 is 0. So that is nothing come up with this. Okay, so there is no use of this because there are only two constants and we got, sorry, this is c3. I'm sorry. This is a third variable c3 here. So that c3 we need to obtain. Since c1 is f of s, so it is x of s0. c1 is f of s, which we got from here, into 0. T is 0, we substituting, plus c3. So This will give me C3 equal to S. So finally the solution we got, it is x of st is equal to t into fx plus s. Y of t we will get, it is y of xt will gives me t, and z of st is f of s. This is the things we got. You just see that c1 is f of s, y is t plus c2. C2 is 0, so it is only t. And x is c1. C1 is f of s into t plus c3. C3 is s. So that's why we have this solution. And from this now, we need to obtain what will be the solution. So we have z of y is this. Let me write what is x. So if I substitute this value, f of s here, that is the value of z. So x is equal to t into z plus s. And the value of t we have y. So we have x is equal to y into fx plus s. Okay, so this is what in xy plane, what will be this represent in xy plane? It will represent a straight line intersecting the x-axis at the point. So this is the, if you compare with a line x is equal to ax, ay plus b. So this is represent a line where the value of a is fx, value of b is s. So it is the represent the straight line, and it is intersecting the x-axis at the point s comma 0. At the same time, a slope of this one at point s comma 0, it is 1 upon fs, and z is a constant of each of them. Okay, let me write this quantity, what we have observed here. So here x is equal to y of f of s plus s. Hence, the characteristic are a straight line intersecting the x-axis at s0, and the slope of the characteristic curve at s comma 0 is 1 upon fs, and z is constant on each of them. We observe that if your value of s is between 0 and 1, then fx is decreasing, because the value of fx we have given is this: in between 0 and 1, the value is 1 minus s. So if your s is between 0 and 1, this fx is decreasing, it is 1 minus x. So what we have obtained here, the slope is 1 upon fx, Since fx is decreasing, this slope 1 upon fx is increasing. Hence, they are intersect each region. Okay? And that is the observation that we can make out from this. Let's have another problem which is known as a Cauchy's problem. Solve the Cauchy problem. For 2zx plus y zy equal to z for initial data, curve is given c is equal to x0 is s, y0 is s square, z0 is s if your value of s is between 1 and 2. So first we need to consider, or we need to find out what is dy0 by ds into p minus dx0 by ds into q. This has to be non-zero. But if you compare with this quasi-linear equation, then the value of p we'll have it is 2, value of q it is y, and value of z, sorry, r is z. y0 is s square. A derivative of that with respect to x will gives me 2s. A value of s is 2 minus x0. The derivative of x0 with respect to x will gives me 1. The value of q is y. So it is 4s minus y. But what is the y? It is s square. So it is actually will have s square. And your s is between 1 and 2. So this will gives me s into 4 minus s, which is not equal to 0 if your s is between 1 and 2. Now we need to consider 3 ordinary differential equations. So consider the system of ODE as dx by dt is equal to 2, that is p, dy by dt is equal to q, which we have it is y, and dz by dt is equal to z, which we have it is z, r which is z. So if you can solve this 3, we'll have x is equal to 2t plus c1, y is equal to, we can apply the separation variable method, we'll have dy by dt is equal to dy. So this will gives me ln y is equal to t plus ln c2. So the y is equal to c2 into e power t. And this will gives me again with the same manner ln z is equal to t plus ln c3. So z is c3 into e power t. Initially given condition, initial curve is given x0 is equal to s, y0 is equal to s square, and z0 is equal to s. So this will gives me, if I substitute t equal to 0 in these 3 equations, will gives me the first equation is 2t is equal to c1. This is the first one. So x0 is equal to 0 plus c1. So c1 is s. In the second equation we have y is equal to c2 e power t. If I substitute 0 here, so y of 0 is equal to c2 e power 0. But y of 0 is s square, so it is s square is equal to c2. So the value of c2 is s square. Z is equal to c3 e power t. Z of this actually s0s, y0s. Z0s is equal to c3 e power 0. So c3 will gives me s. So hence we have x of xt will be 2t plus s. Y of st will be s square e power t, and z of st will be s e power t. Now we need to eliminate s and t from this, and we need to have some equation in terms of x, y, z. That is our objective. So if I divide this two equation, that is this two, y and z. So y by z will gives me s. You just observe, because t will get cancelled out from there. Okay, so we have y by z is equal to s. Now we need to obtain the value of t from this. To get the value of t, what we can do? We can we need to eliminate s and t. So s is removed, that is y by t we get by dividing this s square by e raised to t upon s by t is cancelled. So we have s, we can substitute that one here. Now the t value of t we can get from how we can get t. So from this I can say s is equal to x minus 2t. So let us see what is this xz. Let us see what is xz. Xz we have, that is 2t plus s into z is s into e power t. So that is 2t s e power t plus s square e power t. So s square e power t we already have, that is y. So it is 2t s e power t plus y. So that's why xz minus y is equal to 2t s e power t. And s e power t is z. So this s e power t is z. So I can say that is equal to 2tz. So therefore it is xz minus y upon z is equal to 2t. I take 2 also on this side. So the value of t we can get xz minus y upon 2z. And the value of s we have obtained it, that is y by z. Now we substitute this value of s and t any of these three equations. Let me substitute in in the last equation. So z is equal to, so now we have z is equal to s e power t. The value of s is this, y by z. So it is y by z e power xz minus y upon 2z. So finally we'll have z square is equal to y e power xzy minus 2z is the final answer you will have for this example. Let us solve one more example. So the question is this: solve this zx minus zy plus z equal to 0 for all y and x greater than 0. This is the region is given, and the initial curve it is given x0 is equal to 0, y0 is s, and z0 is minus 2s. If your s is between minus infinity to plus infinity. So the first thing you need to check whether the condition, that is dy0 by ds into p minus dx0 by ds into q, which is non-zero. So we know that the value of p, by comparing this with that, it is 1, value of q will be minus z, and value of r is minus z, because this plus z goes on the other side. y0 is s, the derivative of s with respect to x will gives me 1, the p is 1, minus x0 by s is 0 into q, that is minus z, and this will gives me 1, which is non-zero for any s. So we can say that the solution exists and it is unique. Now consider the system of ODE as dx by dt is equal to p dy by dt is equal to r dz by dt. Sorry, dy by dt is q and dz by dt is r. So dx by dt, the value of p we have here, so p is 1, dy by dt it is q, which we have minus z, and dz by dt is also minus z. Now we need to solve this three equation. So solving the first equation, we'll have z is equal to, dz by z is equal to minus dt. So it is ln z is equal to minus t plus some constant ln c1. So z is equal to c1 e power minus t. This is the things we got. And from this it is x is equal to t plus c2 we get from the dx by dt is equal to 1. Taking integration, we'll have this. Now to obtain this one, we'll substitute this value, the value of z, as c1 e power minus t here. So it is, we'll have it is c1 e raised to minus t, integration by parts, separable variable method. We'll have this y is equal to c1 e raised to minus t minus plus c2. Now using the initial conditions, we need to obtain this c1, c2 and c3 is here. So using initial condition, that is x0 it is given is 0, y0 s comma 0 is s, z0 s comma 0 is minus 2t. What we have is this x is equal to t plus c2. We use this one, that is x of s0 is 0 plus c2, so the gives me c2 is 0. Z equal to, we have c1 e power minus t. So z of s0 is equal to c1 e power 0, but this is minus 2s, so c1 is minus 2s. And y we have, it is minus c1 e power minus t minus c1 e power minus t plus c3. c1 value we already obtained, that is minus 2s e power minus t plus c3. This is y. Y of s0, if I substitute 0 here, that is minus 2 plus c3. But this will be s. So it is s is equal to minus 2s plus c3. So the c3 is 3s. So finally we have x, which will have t, because it is t plus c2, c2 is 0. Y is equal to c1 plus e power t plus c3. c1 is this minus 2s, so that is minus minus. So it is minus plus, yeah, minus is there. So it is minus 2s e power minus t plus 3s. And z we have, that is c1 e raised to minus t. So it is minus 2s e power minus t. Now ultimate goal is to obtain the value. So we already have the value of t. We need to solve this equations and we need to get value of, or we need to eliminate s and t from this. That is our objective. We already have the t in terms of x. Using this two, y and z, we need to obtain the value of s. You just observe that this minus 2s e power t is already z. If I use that one here, this is the value of z we have. So we get the value of s from here. So we have x is equal to t, and we have y is equal to minus 2s e power minus t plus 3s, and z is equal to minus 2s e power t. So this value we have here, so that is y is equal to z plus 3s. So s will be y minus z by 3. And if you substitute this value of t and s into the any of this equation, let me put it here. So we'll have z equal to minus 2s, s is this y minus z by 3, e power minus x is the final answer of this we can have. Yeah, we need to calculate for, sorry, this we need to solve for x only, not y, not z should be there. This I need to calculate for only x and y. So for that, need to work out. So the value of x, so this will gives me z is equal to minus 2s e power x. Okay, so this is also we have minus 2s e power s minus t is there. This minus t minus x plus 3s. S is common out from this. S minus 2 e power minus x plus 3. So the value of s from here will have from here we have y upon 3 minus 2 e power minus x. and if I substitute that value of t and s here, so z is equal to minus 2 into y upon 3 minus 2 e power minus x into e power minus x. So this is the solution we have, final answer we get. So that's it for today. If you have any questions, you can ask.